Hello, this video is on section 7.7, which I do believe is the last one of this chapter, which is titled Exponential Growth and Decay. And the target, as you would expect, is very self-explanatory from the section title, is to model exponential growth and decay. So the first different type that we're going to talk about is a growth. Now, an exponential growth still follows the exact same general form of an exponential function that we've talked about already, which is y equals a times b raised to the x power, where your x is your variable. And then some criteria on a, where again your a is still, it's going to be greater than 0, where it starts out at a positive value. And then your b must be bigger than 1. In order for this to be a growth or an increasing exponential function, your b must be greater than 1. It can't be less than 1 or greater than 0. Now, the number that determines how quickly and how sharply your exponential graph is increasing or growing is your b value. And your b value is the same thing as 1 plus the percent rate change in decimal form. So if your graph is exponentially increasing by, let's say, 50%, as a decimal form, that means you find the decimal placeholder, move it to the left 2 points, so it now becomes 0.5 instead of as a percent value. And to get your growth factor, you have to add 1 plus that number. So it becomes 1.5 is your growth factor, which still satisfies the value of b is greater than 1. 1.5 is bigger than 1. Now your a is going to be something else, but that's just the growth factor when it comes to it. So looking at each individual piece of an exponential growth, your a is the initial amount, or the value when your x is equal to 0, which in most cases is going to be time. When time is equal to 0, that's your initial amount. Your x is your exponent value, and the b again is your base, which is going to be greater than 1 and known as the growth factor. Now we'll go through some few examples on the difference between growth and decay, but before we get into decay, there's a very, very important, I guess most useful exponential equation growth that everyone will be using at some point in their life, and that's calculating compounding interest. Now, compounding interest is a way for you to put some money into a savings account, and with a certain interest rate and compounding number of times, that bank account will accumulate money just sitting in the account and not doing anything else. Now, you may put some more in there, but that money will be making money inside the account. And the formula for that is a equals p times 1 plus r over n. All of that is being raised to the n times t power. These two numbers are being multiplied. Now, each of the letters represents something. The a is your final balance, or the final amount that you're trying to calculate for. Your p is equal to your principal, which is also the initial amount, so the amount of money you put into it, or you initially put into the account and start out with. Your ray is your r, is your annual interest rate, and the annual interest rate cannot be written in percentage form. It has to be in decimal. So like the last example that I went over, which was converting, I think it was 50% into decimal form, that means it's 0.5 or 0.5. M is equal to the number of times interest is compounded per year. So there's a few different words that you'll see when it comes to compounded per year. If you see the word annual, that means it's 1 time per year. Biannual is 2 times per year. Some other ones you will see is monthly. If it's compounded every month, that means it's compounded however many months there are in a year, so it would be 12. And then daily, which we probably will see less often, but that'd be 365 because there's 365 days in a year. And then t is your time in years. If you're given a date and a time in days or months, you have to convert that to years. So it's very important that that is your unit of time that you are using in the compounding interest formula. And a lot of these are going to be very word problem focused examples, and it's just kind of plugging these values in of the principal, the rate, number of times, and the time in order to get your final balance. This is very useful in order to check to make sure the banks are showing the correct amount of money you should be accumulating with this interest rate, because sometimes they may throw in a few fees that aren't specifically stated in your bank statement that try and trick you into your amount. So it's always nice to double check what your value should be. Then the other half of the learning target is a decay, and that's exactly the same thing as a growth in terms of using the same exponential formula or function equation. The only thing that's different with this one is that your b value is between the values of 0 and 1. So it's any positive rational number with a numerator of that's less than 1. So it could be 1/2, 2/3, 4/5. Those are all examples that fit into this array of bigger than 0, less than 1. And just like we had a growth factor, we also have a decay factor, which is representative of the same thing in your equation. The only thing that's different is you're taking 1 minus your percent change or your rate in decimal form. So taking your percent, converting it into a decimal, and taking 1 minus that number will give you your decay factor, and it's always going to be between 0 and 1. Always, 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 if it's going to be an exponential decay function. So it's really important that you're getting down what each of these values represent, especially this formula right here, and knowing the difference between growth and decay. That growth has a b value greater than 1, and that decay has a b value between 0 and 1. Those are the most important things that you can write down from this video. So we'll go through some examples, some word problems in class to make sure you're a bit more comfortable, but that's all I've got for you guys. All right, thank you.